Good afternoon to everyone. I welcome everybody who come today to join us to our monthly webinar. For those that join us today for the first time, my name is Jean-Michel Ting. I am the program coordinator of TraCR, which is the Transportation Cybersecurity and Resiliency. So for those that join us today for the first time, TraCR is a US DOT national funded transportation center led by Clemson University in collaboration with 9 other prestigious universities across the country. And I will let the floor to the CEO, Dr. Mashrur Ronnie Chaudhary.
Hi, good afternoon. This is Ronnie Chaudhary. I'm the director of the National Center TraCR. It is my pleasure to welcome a prestigious scholar as well as my close friend, Dr. Yinhai Wang. So here is a short bio of Dr. Yinhai Wang. Dr. Yinhai Wang is a professor in transportation engineering at Civil and Environmental Engineering and an adjunct professor at Electrical and Computer Engineering of the University of Washington. He has served as director for Pacific Northwest Transportation Consortium or PACTRANS and also in 2012, since 2012, and for the Northwestern Tribal Technical Assistance Program since 2022, and the Washington State Transportation Center since 2023. Dr. Wang was an elected governor for the IEEE ITS Society from 2011 and through 2014. I think I also served at the same time frame, the Board of Governors. And he served as the 2018 to 2019 president of the Transportation and Development Institute for American Society of Civil Engineers. He chaired the AI and Advanced Computing Applications Committee for TRB from 2021 through 2025. He's currently chair of the ASC Center for Technical Advancement, president for the Council of University Transportation Centers, co-editor-in-chief of the AI for Transportation Journal, and the Connected and Automated Transportation Special Section editor for ASCE Journal of Transportation Engineering Part A Systems. His active research include computational methods, data analytics, traffic sensing, data quality control, transportation safety, transportation data science, edge computing, among others. He is a professional engineer registered in Washington, State of Washington, a member of the Washington State Academy of Sciences, a distinguished member of ASC, and a fellow of both IEEE and IT. He has been recognized by numerous awards, such as the 2025 IEEE ITS Outstanding Research Award, 2023 ASC Francis C. Turner Award, and the IT Innovation in Education Award in 2018. He will talk to us today on the topic of advances and challenges in using Edge AI to address transportation safety challenges. Like the audience online, I'm really looking forward to Dr. Wang's presentation. Thank you.
Thank you, Ronnie, for the kind introduction and also invitation. It's my great honor to speak to your center. So I'm so happy to see many familiar faces and names. So today I want to share with you my view and research on Edge AI. So the title of my presentation, Advances and Challenges in Using Edge AI to Address Transportation Safety Challenges. I do see this as a lot of potential, but what we've been doing is, just the beginning of this entire domain. So I would encourage more of you try to, do something in this particular area. Maybe you heard about a lot of discussions about transportation safety and whether like a traffic crashes are considered a kind of a perfect crime. So there, the 1965 short film by Robert Altman, if you have not watched that, I would encourage you to look at that. There's also the 2014 like Freakonomics radio episode 165 also talk about the same thing. So obviously, transportation safety is important focus of our transportation society and also everybody's daily life. Looking at, the past 100 years of effort, I say past 100 years is because you see this like a William Phelps, he actually started his work. He published a book in 1903 about the rules of roads. But I made a big effort. I cannot find any picture about it. Instead, I found another work from him, like the street traffic regulations published in 1909. If you consider transportation safety research started 1903, getting to today, we have over 120 years of history, right? So this is history pretty long. But looking at our observations about transportation safety, we still get about 40,000 people killed in the United States. And this is way too high. So certainly, even we see the like fatality rate, maybe for vehicle miles of travel, that decreased. But since basically 50 years ago, this like decrease is very slow, right? It's almost flat. So we've got to think about, are we on the right track? Looking at the same time period, right? So let's say in 1939, that's the first kind of computer. Basically, that's based on the relays, do some simple addition. So this is the Model K because this guy actually developed this in the kitchen. So that's very simple and a poor computer, right? Until 1955, this first computer runs the first program using like the 12-hole like paper tape, try to input the program, and the system is able to operate. You can see the size of this particular computer, right? So, but getting to 2025, and this NVIDIA's the most recent Jetson AGX Thor, this is the most powerful edge computing device. So you just see like the progress of the computer science has been amazing, right? The computer hardware and software, you can see like in the 1940s all the way down to 2020, right? Advancement of AI and quantum computing. There's just a lot of progress. We can notice the size change, the computing speed changes. If we consider, computer is just purely something physics, right? So let's look at something related to human. Again, for 100 years, right? Let's count from, let's say, 1900 to about 2011, right? So the life expectancy by year, so that was like 48.3 in 1900. To 2011, that's 78.7. So that's a lot of improvement also. But why traffic safety has not been improved at the same pace? So we often got people ask us, hey, you guys, transportation safety has been the top priority for the researchers and the agencies, right? We've been making over 100 years of effort. Why we are not progressing, as we would expect? I don't think this is impossible because I listened to some international speakers and some of them gave me some good examples, like in a particular city, a Tongji University team, they actually diagnosed the roadway geometries and other things and recommended the local government to make some changes. And then the government implemented the solutions, the number of fatalities dropped from 17 to 1. It's just in less than 10 years. So I think we could do something, but exactly what's wrong? Why, we're not improving transportation safety to the desired level? So not only the fatality fluctuate at around 40,000 people a year. If you look at pedestrian and bicycle fatalities, they have been increasing since about 2010. And this is horrible, right? So exactly what's the problem? We know we have better vehicles, we have better sensors, but why do we still see the increase of these fatalities? Let me show you a video. This is actually a very big traffic crash happened on I-81 near the Hagen exit in Pennsylvania. So let me briefly show you this video so you get an idea about the type.
This is ridiculous. It's snow and fog mixed together, and it made the visibility down to 0. And oh, watch out, watch out! Oh, God! My car is gone! I need to get all my shit out of my car, but it's too dangerous. And it's on fire! Oh, look at that! I need to get off the road!
So this is the video I downloaded from YouTube. So basically, you can see this particular crash happened in a snowing day. The roadway surface is very slippery, and more importantly, the visibility is almost 0, right? So could we do something, to prevent this 50+ car crash, right? This 6 people got killed in this particular crash. We can see, the happening of this, particular crash. This YouTube video is over 3 minutes long, but it's not from the beginning of the crash, nor to the end of the crash. So I think there's a portion of that. But over, let's say, multi-minutes time period, could we do something? So let's keep this question in mind, and then we can revisit this later. What are the most effective, safety solutions, right? So certainly different field of people would have solutions from different perspectives, like education, regulation. So we're engineers, right? Let's look at from the engineering perspective, what are the possible solutions? So the US DOT considered connected vehicle technologies can potentially reduce up to 80% of the unimpaired crashes. So the connected vehicle concept, maybe you are familiar with that, right? So basically, if anything happened, let's say there's a particular crash happened here, and this will be reported to the roadside unit, and the roadside unit will be transferring this to traffic control center, and traffic control center will decide what to do, what kind of information to push to the roadway users. And then vehicles will be following, the new guidance and try to avoid, another crash or make the congestion mitigated. So that's an idea. But this idea was raised, I think, 30 years ago. But if you look at, what is the impact after so many pilot projects? So we have to question exactly, maybe something is missing or something is not quite right. So let's look at this particular map. The yellow colors are basically the operational connected vehicle projects. And the green ones are actually the planned size. So there's a total of 13,000, projects or size. We do not know exactly what kind of a positive impact has been generated. At least we did not see, the news media is reporting, hey, there's a safety improvement or there's a crash awarded because of this, particular connected vehicle project. So we have to revisit exactly what kind of impact has been generated from these investments. But if you look at the current technology, so I can raise some question immediately about the design of the system. I think there are some fundamental issues. Let's say the roadside unit is designed to communicate with onboard unit, with vehicles, and also communicate with the traffic control center. It cannot communicate with people's cell phone, And therefore, if you are a pedestrian or bicyclist, you may not be able to share information or interact with the system. You know, on our roadway, we have a lot of traffic sensors deployed. And these traffic sensors are serving for the purpose of detecting vehicles to serve like the traffic signal control or collect some data, right? So these sensors will be responsible to traffic controller or the traffic control engineer. They purchase the sensors, right? The manufacturers of the sensors do not see themselves have the responsibility to feed like the roadside unit. And then the roadside unit ended up to be actually hungry for information, right? Even let's say you get somebody pushing information to you, say there's a crash here. And all this roadside unit could be doing will be sending the information to the traffic control center, right? So that's purely the communication function. There's no detection function with these units. And at the traffic control center, I don't believe in the current stage, the traffic operators would know what to do. Let's say there's a crash on a particular street. Unless you have very good sensor coverage on the entire network, and these traffic operators are very well trained, and there's a supporting model predicting what's going to happen, these people may not be able to deliver, you know, what kind of message to show on the variable traffic message sign or like a pass to the roadway users. I think that's another important thing. So basically, these roadside unit may cost you $5,000 to $8,000 a unit, but they're hung up there, also need maintenance, but they cannot receive much information. So I think if I were a city traffic engineer, I'll be really cautious in deploying them, because after you deploy them, you have to spend money to maintain it. If you don't have all the sensors supporting it, or if my neighbor cities don't have these things, they may not be really showing the benefit expected. So that's a problem number one. Another problem with these things is, let's say you have some roadside unit, even you count on it to collect some information and transfer, right? There's always delays, you know, the latency, right? Depending on the communication system's availability or the bandwidth, it may not be able to deliver the information timely. But for traffic applications, we really want almost real-time response, right? Otherwise, it could be really dangerous. So that's another issue with this current roadside unit. You rather than, you know, just the hardware issue, right? So we also have other problems. You know, for example, there are some places with the sensor redundancy, maybe multiple sensors deployed for different purposes, but they overlap each other, right? But if you want to make a good use of all these sensor data, you will find actually these sensors each have their own data stream and data format, time resolution. So it's very hard for the end users to be integrating them together. So that's creating actually a problem for the end user. At the same time, there are like not many sensors measuring important variables like how far drivers can see, like the weather stations. In the entire Washington state, we only have 180 weather stations. And very few places there are like traffic sensors measuring the visibility distance. Like the left side picture is an example of this. And these systems are pretty expensive, like $30,000 or more. So if these important data are missing, that creates another issue, right? So when we try to manage the roadway, we don't have this important information. How do we, you know, set up the right strategy and use the connected vehicle sensor network to best serve the roadway users? So thinking all about these things, we consider in-the-ball real-time perception and the reasoning at the on-site device. It could be roadside unit or other things. It's quite important. Let's say we have a smart device. We call it smart hub. This smart hub is able to communicate with onboard unit and also communicate with users, like a user cell phone, and also be able to communicate with traffic management center. But in a lot of scenarios, you may not need really communicate with them unless your entire roadway network is being covered with sensors and the roadside unit. If you only have, for example, a very dangerous roadway curve, maybe you observe a lot of departure crashes due to maybe black ice or slippery road surface. If you deploy a device there monitoring this particular section of the road, and if you see like the visibility is poor, if you see the road surface covered by black ice, you just inform maybe the roadway users, right? And that's enough. You don't need really to send information to the like a traffic management center. And in the rural places, you may not have such a center, right? Or your communication system may not be able to support such applications. So we consider maybe if we can make this smart hub to have like the perception function, you can understand the traffic environment well and be able to do some inference and be able to interact with users. And that's a perfect device to fit in this area and be able to communicate back and forth, try to improve like transportation safety. And the perfect technology, in my opinion, is this, edge AI. Basically, that's the artificial intelligence on the edge computing device. Maybe you wonder what is edge AI. So basically, edge computing is the computational processing of sensor data away from the centralized nodes like the servers or cloud and close to the logical edge of the network. Let's say on the transportation network, you have an edge device at the intersection collecting the vehicle's arrival departure information and do the computation there just on the device. You avoid sending a large chunk of data back and forth to the cloud or to the server, right? So you can save the communication costs and also reduce the latency. So there are certainly a lot of advantages with the edge computing, right? It also has a weakness, right? I will talk about the challenges later. So edge computing is very effective in addressing the growing demand for computing services because we need this kind of computing like system to collect local data, like sense the weather, like collecting traffic, and edge computing devices will be a good fit. They are not expensive and they can easily be deployed. And they are very cost effective in data processing because you don't need to be sending data back and forth. You got reduced communication bandwidth and cost, reduced computational load at the centralized cloud server, and reduced data storage needs. Because after you process the data, a lot of data could be safely dropped, right? You only keep the most important information you want to keep. It's really well suited for large-scale applications and the rural area where the communication systems are very slow. And also, from the privacy protection perspective, you got the data collected and computed, and you have no sensitive information sent out, and you can protect the privacy better. In the European countries, they do not allow like images sent out from their devices. So we collaborated with Norwegian Public Road Administration. We actually tested some of our technologies there. We got, the video camera collected some video images. We processed that, delete the image, only send like the traffic volume, travel time. I think that would be a perfect fine with them. If you send videos to the cloud or the server, that would be a problem. That's a violation of the privacy policy. Yeah, as I mentioned, because the data is processed locally, the response time is fast, right? So we reduce the latency. In my research lab, the University of Washington Smart Transportation Applications and Research Lab, we've been studying this issue over the past 15 years. So we developed a technology called a mobile unit for sensing traffic. This particular technology is an innovative Internet of Things technology for comprehensive traffic sensing and vehicle-to-everything applications. So it increased, like the computer vision, environmental sensing, like edge computing, and AI, a bunch of technologies all together. And this could serve as like a roadside unit or a sensor, right? If you combine the two together, roadside unit is no longer having, the data starving problem. And because you handle all these things together, you avoid, the data consolidation issue, right? Because you measure things on the same place, on the same device, and you understand exactly the resolution of each data set. You can also try to use the same data format, make the consolidation much easier. So this particular technology is being developed and tested in a lot of locations. So at this moment, we have like the data collection, data fusion, all happen on the same device. And then we do the data analysis using the same data stream, right? So we don't have the format problem or other issues. And so that makes the end user a lot easier and happier. So in addition to like a sensing and collecting data, this particular technology can also be used to interact with road users, right? That's the communication function like a roadside unit. You can also control like a variable message sign or other devices. So we have been using this technology to control like the avalanche sensors that we have another project collaborating with Washington State DOT. And this is also funded by the TRB Highway Idea program. So, the functionality of this edge system is really, I think is unlimited. It could be used for a lot of different purposes. So here are some quick examples about, what this particular system has been developed for like transportation purposes, like traffic sensing and counting. And the accuracy is pretty good, as you can see in the table. Another important thing, it can detect road surface condition. You don't need to be having a road surface sensor to detect if the road surface is covered by black ice or not, or snow. So this particular machine learning based approach could sense the road surface picture, identify where is the road traffic lane. So whether this is dry or wet, or covered by black ice. I think the systems have been working also pretty well. Due to the time constraint, I will not stop for too long on each slide. If you're interested, we can discuss offline. I want to save some time at the end so we can discuss about some issues of common interest. I mentioned the current roadway system is lack of like visibility data, right? So this particular picture shows a sensor. If you buy it, it's like several tens of $1,000s. But if you use a video camera, it could be a surveillance video camera, or the camera come with the master sensor, use some technology. We have this particular technology. Actually, we created this, and this is in the process of patenting. You can see this original image, right? So this image, and we use our technology, try to extract like the scattering map, that's the middle. This is actually the airborne articles preventing people to see the road surface clearly. Right? So if we extract such a map, and you can see the processed image is very clear. You can see very well, right? So by looking at the density of this scattering map, we'll be able to see, how far a driver can see. So this is not really very, very accurate, but I think it's enough for our transportation operation purposes. Here's the data, right? So let's say if you look at the visibility between 1,000 to 2,000 meters, so it's like a 90% chance you get this within 5% error. So in addition to these simple functions, like to collect traffic information, to count, right? Or like classify vehicles, detecting road surface conditions, we can also use, the sensors deployed at different locations, try to match the vehicles without using the license plate, simply looking at the vehicle and try to match them. If we do have the successful matches, then we get like the travel time, right? So And the travel time information is very important, right? So you can see actually this is actually the technology we have already developed with over 90% accuracy in matching. So even the camera is installed at different locations, the camera's color may not be exactly the same, and the cameras may not be facing the same direction, right? So you can see actually there's still vehicles pass through different locations, get detected. Right, to 69, go this way, and in this camera, go to it the other way. Classifying like vehicles into the 13 categories as required by the federal highway is not an easy task. In Washington State, we have about maybe several hundred, we call it traffic count locations using like loop detectors combined with piezo sensors try to collect such data. The installation of these sensors will need to interrupt traffic, right? You need to block the traffic, do the sensor installation, and maintaining the sensors will also be, requiring like the closure of roadway. What about if we use like the master sensor, just use the video camera and machine learning, try to identify like the vehicle's exact class, right? So this actually shows our result. We got like a 97.6% accuracy. And this is the daytime. We're still working on the nighttime condition. I think our nighttime condition is also getting close to 90% accuracy, but we're still working on that. And compared to the best claimed result so far by some company, like that's 96%, I think we actually outperform this best product off the market. Yeah, so at the intersection monitoring, right, you could see like vehicles coming from different directions, how many near misses are there, and why there's a particular near miss, right? So we can also do the cooperative sensing. So this is actually some applications we've been doing at multiple intersections. The result is also very encouraging. It could be used for a variety of purposes. Now, in addition to this data collection and the communication function, you also want to allow, for example, transportation agencies to be able to see what's going on at each location, what kind of issues are there. So we built a phone app, and this phone app could access, the locations of these traffic sensors, like the master sensors. Like this is actually the pilot project with the city of Bellevue. And you see actually the city of Bellevue has like 3 sensors deployed along this Mountain Lake Boulevard. And this roadway has, like sometimes 10% of the grade. It's pretty steep roadway and near the forest and lake. Very often you see like black ice on the surface. There are multiple traffic crashes a year. So what the city did was to put surveillance cameras on each of the poles they have. And I asked them, did you do anything? They say, we have no person to watch these things. And then we recommended, try our technology. So this technology install the sensor, it will be monitoring the road, collecting traffic data. If you see any issues, right, it will be generating warning. Let's say if the road is covered by black ice, it will be generating a road surface hazard warning. Or some incident occurred, will be generate an instant warning, right? So this warning message could be sent to the traffic operators, by email, by short message. And the device can also communicate with people getting to this area, like what kind of hazard is downstream, right? So make drivers prepared. We deploy this technology at the Yakama Nation, which is federated tribe in Washington State. Highway 97 goes through the tribal land, and this roadway is considered the deadest highway. And this particular highway actually have like just 60 miles road from Union Gap to Toppenish. There are over 20 serious crashes. So when we suggest the technology and the tribe council voted this and unanimously passed, to install the technology. And this was deployed at the intersection Lockery Road with like US 97. This intersection got 7 people killed over the past 20 years. It's the most dangerous intersection. So after we put up the sensor, there are a lot of local news report about that, and they feel very excited. And over the past several years, the sensor's been there for multiple years. Actually, we observe a lot of valuable data. We found over 70% of the vehicles using this particular intersection are large vehicles like trucks or agricultural vehicles, while the intersection is designed for smaller vehicles. You see there's no pedestrian walk, but there are also pedestrian interactions. In the winter time, very often the roadway is covered by ice or snow, and the visibility is very, very poor. So all these data actually are very valuable information for like the tribal government and the Washington State DOT to do something together. We use the data, we apply for a SMART grant. We got the project. We're working on expanding the project to cover the 60 miles road and also using a digital twin to address the challenges. So this project's in progress, and maybe next year I will be able to report that project's findings and the effectiveness of the technology. We got a lot of recognitions, like we received a US DOT like a Build a Better Mousetrap Innovative Project Award in 2023. And that's also the best project all year round. Earlier this year, we also received the Washington Traffic Safety Commission's Safe System Champion Award. So that's a good encouragement to our team and also our collaborators. At the same time, I think we also put in a lot of hope for this new technology to be able to help improve transportation safety. Hopefully, we see some really encouraging results and maybe at least make one effective safety solution available for people who are interested to address their challenges. And this particular technology has been, carried to practice by some of my postdocs and students, and they formed this company called AI Vision, and they receive a lot of recognitions like the startup label finalist, and they were invited to be talking, joining teams. So it's a good thing to see like our University Transportation Center research to be generating the practical impact in our practice. So that's a quick thing about, what I believe the Edge AI will be really helpful for like addressing the transportation safety challenges. And we demonstrated that it is effective, right? We use, at the very beginning, we use Raspberry Pi, and now we're using NVIDIA Nano. So these are not the top, edge computing devices, but we make it work, right? As you see the results, it's just presented. But there's still a lot of challenges, and this is a good fit for like your center, and also I think Professor Yunpeng Zhang's center addressing the cybersecurity issues. There are a bunch of issues, need you guys to contribute, right? So I see, the challenges with this technology include resource limits, device heterogeneity, because these edge devices are very different, right? The functions, the capability, the price, and there are various scenarios, like different situations may require, the computing from different perspectives, or maybe emphasizing different functions using different approach. Cybersecurity risk, when you have a lot of smaller devices deployed over a network, and their computing power is so limited, you may not be really implement a very powerful security solution, right? How do we address the security challenge? And also the sensor degradation, like when you put the sensor at different locations, due to the sensor's initial hardware issues or other problems, you may see the sensors not collecting data at the level of quality we expect, right? So how do we address those challenges? Given the time constraint, I will just briefly mention all these things, right? First of all, the resource limitation, right? So how do we address it? You see, like, so I use the Jetson Nano as the edge computing device example, and A100 GPU. None of these are the latest, right? But they are representative, widely used. You can see the computing power difference, right? For the Jetson Nano, that's 472 like a GFLOPS is basically a gig, like a floating point operation per second, right? So for the GPU, that's like 312 tera, right? So tera to gig, that's the difference. Memory, computing power, latency, right? So there are a bunch of differences. I don't want to go to the details, but you know, the central computing equipment versus the edge computing equipment, their computing power and the computing resources are very, very different. So how do we address this resource limits, right? So there are different approaches, right? So here, just give you example, like the lightweight models. You have to design the lightweight models. You cannot just grab a model from, you know, the general models created by the computer scientists and implement on your edge system. That's not going to work, or it's going to be work very, very poorly. So we need to be doing the small architecture design, also do the knowledge distillation, model quantization, and model priming. So these are basically try to make a complicated model like a simpler, or like cut down the unnecessary branches. Here, this chart is showing like a original model. You can consider this is a teacher model, right? You do the knowledge transfer. You do like the distillation and then transfer. You got a student model. This student model is basically simplified, a smaller size, ready to deploy on the edge computing device. It will fit and make it work. If you use this original model, it will not be working. Another important approach is to optimize computational resource usage. Here, this example we found from this paper published here, like it's talking about, you know, these different steps, right? And you can see if you implement these steps, there's a significant impact, like initial stage. If you do the static dynamic transformation, so that's like 15% drop of the memory usage. And then you could do like unused data removal. That's another like 32%. So basically you see the impact for taking each step, right? You have to be doing these things in order for a general approach to work in your edge computing environment. The second challenge is like the device heterogeneity, right? So different edge computing devices, they are designed differently with different configurations of the hardware. So normally what we do will be the model level solution. So you do the hardware aware, like a neural architecture search, figure out, you know, what are the constraints, what is allowed, what's not allowed. And then you try to optimize your approach operation on this particular device. And here you could use this so-called once for all system network, right? So you can train like a different models, right? A model for a larger, like a larger size, fit for a better, you know, or more powerful edge device, or the small one, or the tiny one, right? So you could be doing different training at one time. And then when you need to deploy, you identify what kind of device is this, and then you choose the right model to run on that particular device. And here that actually shows the CO2 emission, right? So if you try to do this once for all on edge computing, the cut down of the CO2 emission is significant. Another way to address this device heterogeneity problem is the model deployment solution. As I said, you know, you could train like a once for all, right? So get the model, and then you could be like also use other technologies. For example, try to do the post-training quantization, you know, reduce the precision waste, like changing like the high resolution like a data type to like a lower resolution data type to save, you know, the amount of operations. Or like you can do the priming, right? So cut down the unnecessary branches of the model to make it work more efficiently. The third challenge is scenario variations, right? So like in some scenarios, you don't gather enough data. Let's say if you want to train a model to recognize pedestrians, very often you see a lot of walking pedestrians, very few wheelchair users, right? So how do you address that challenge? And some approach is a so-called data augmentation, right? By rotating the data, you could create some other scenarios. But please keep in your mind, no matter how you do the transformation, that data is not like the independent observation, right? But it could be somehow addressing the model's unbiased, sample weight problem. So let's say you make the data sample size at the right level, and you can use that for training. You could look at different conditions to use the model. You can have different kind of models available for deployment. And you could choose to use, for example, condition B in a certain scenario, and condition A in other scenarios. Yeah, so another method is the multi-model sensor fusion, right? It's just like in our connected vehicle setting, you have a lot of different sensors and collecting information from different angles, different type of the roadway object, and then you can combine your vision together, try to address this kind of scenario variations. And the fourth problem, the cybersecurity. You people are the expert on this, right? So we did not really do much on this. It's just we recognize this as a very important thing, right? So the attack could happen at different levels. Let's say expanded attack surface, right? You have a lot of edge devices deployed over the network. Every device could be a potential target. And the man in the middle, like attackers, could intercept the communications between two devices and make an attack, like a distributed denial of service. Maybe you people are familiar with this. I don't want to go to the details. Like a V2S communication attack. Also, AI model inversion. AI model inversion is, they attack your device and try to modify the data. And when the data used to train the model is changed, they could mislead the model, right? So that's another potential cybersecurity risk. And data breach, unauthorized access, theft of the sensitive information, etc. So these are all the cybersecurity challenges. And for the edge computing environment, this is more severe challenge than the cloud computing. Sensor degradation, I think this is something as I mentioned, right? So when you deploy the sensors after the door, a lot of factors will be affecting, how the sensors work. And you could be using these different approaches like self-diagnostic and recalibration algorithm, try to find these problems and rebalance like the color and other things. Or you can do like some pre-processing, like this is the input image using your and the ULO kind of message perform better for a regular image, right? You could use some approach, try to repair the image, like this is the repaired, and you input this one to process by the ULO model. The result could be much, much better. So anyway, so those are the key challenges that we identified through our research. Another important thing to make a successful application of edge AI is actually try to customize the model, right? So this is actually a live video we got from the YouTube, and this is a camera installed in some street in Shinjuku in Japan. You can see like individuals walking in this detection area indicated by the red box can be easily detected. And this is just a regular approach you take off the shelf from like the computer like a community, and that works. But if you look at this scenario, right? So in transportation, we often face, more challenging scenarios. This is like a lot of people in the scene. And how to recognize people? You use this general computer science model, is not going to work, right? So, but we did compare the two approaches, right? So this is just implement the YOLO approach directly for like this is also in Japan, like at the intersection. You see most of the pedestrians are actually missed, but we developed our own approach called SARLIS system. And this one, we actually implemented our transportation domain knowledge to modify the general model of the computer science. You can see actually almost every pedestrian or bicyclist are detected. So the performance is way better than this YOLO V11 approach. So exactly what we did to implement, the approach to make it perform better. So this is actually, we use our approach. We know the intersection approach, closer to the intersection, you see bigger object, right? When they are far away, they are smaller. And we have to use different approaches, try to find how many people are there. We use the so-called density map, right? So this is the approach, encoder, decoder, and density map. If you want to know more about this, I do believe we have a paper published this. I forgot to put the paper source here, but I can give that as needed. And through our practice, we also summarize what is the right approach to use, right? So this is actually, we summarize how can we, do a good job developing edge AI approach with our customized, AI models. So this is the procedure. I don't want to go through all these things. I believe, these things are available for you people. You can watch this and see, look at this and see if you have suggestions to improve, right? And you could try this to see if that works in your research, try to build a customized edge AI model. Now let's revisit the example we brought up at the beginning, right? So this big intersection, this big traffic crash with over 50 cars involved and 6 people killed. Let's say when the snowfall begins, we are able to tell there is a visibility degradation, right? If the visibility is low enough, we should trigger a visibility warning, right? Using the master sensor technology I just presented. When there's enough snow fall on the road surface, right? We could generate a road surface condition warning. When the first crash occurred, we could generate an instant warning. So there are multiple approaches to detect and trigger some actions to prevent this tragedy from happening again. I think the technologies are available, but we need to improve the technology and also increase the deployment of the technology. So we could reduce the number of crashes. Hopefully we can catch up, the pace with other domains, to improve the safety condition, just like the medical science people improve human life expectancy. So in summary, I consider edge AI has been proven effective with a huge potential in safety and mobility enhancement. And edge AI empowered system are the future key elements of smart infrastructure systems. You want the system to be having information, the computing power near the site, right? So I think the edge AI will fit that very well. And it can also support autonomous driving and connected vehicle applications. You don't need to rely everything to be computed on autonomous cars because that's too much waste of energy. A lot of common things could be computed on the infrastructure and share with the autonomous vehicles through V2X. And transportation domain expertise are essential for successful edge AI applications. We need to be really integrating our transportation knowledge into the model development, not just grab a model and use, right? So I think this is quite important through our practice. And this may be the most important thing to make a successful application. And research spending on edge AI method and tool development are likely to increase in the coming years, right? So I do consider this means some good opportunities coming up. At the end, I want to appreciate my team members, like my postdoc, Dr. Mohammed Karim, and my PhD students. Some of them already graduated, some of them are still in process. Actually, they are the driving force of this particular research. So I've stopped here and open for questions. Thank you.
Thank you, Yinhai. It was a wonderful presentation. I learned a lot from it as well. So please, if you have any question, write it in the chat box. But now I have the privilege to ask you for the first question. So Yinhai, you mentioned that the challenges of using the CV2X radios in sending, say, alert or some message to your cell phone. But it is possible, right? So because you have this in the radio, you have the Wi-Fi option, LT option, And also we have tested with the Android phone, we can actually send alert like pedestrian safety. So it is possible like to send data to cell phone from radios.
Yes, now it is possible. The previous DSRC is not
Yes,
supported
exactly.
by electronic devices.
Yeah.
But now the problem is it's kind of messy, right? There's a lot of different ways to do the same thing.
Yeah.
And I hope there will be a more standardized procedure for people to do that.
Yes.
Very often, people consider car transportations are way above other things, right? So the priority is normally given to vehicles, the onboard
Right.
unit. But
Right.
as you can see, there's a quick increase of the pedestrian and bicyclist fatalities on our road, right? So I think we got to be considering how we could make the connected vehicle system benefit the pedestrian and the bicyclist.
Yeah. Thank you.
Thank you.
Okay, I will go ahead and read the question from the chat box. So this question comes from Dr. Latiful Khan. He said, how did handle environmental changes in machine learning algorithm? That's the first question.
How to address environmental changes in the AI models?
And he said he meant the concept drift. How about your data set? Is it simulated data?
No, actually, we did not use simulated data, but for our applications in Norway, right? So we collect a lot of data from Washington State DOT surveillance cameras. They actually outreach me, say, why you guys keep downloading data? We got tens of thousands of images and use for training. We have to do the transfer learning, right, to fit in the local environment. So there's just a lot of energies and challenges. That's why I consider if we have enough people doing this, we share these like labeled images, and that will make the effort a lot easier. Not sure if I answered your question about this.
Weather, yeah. So there's another question of the weather, like.
Yes.
Yeah.
Oh yes. The other one is say, how do you handle? This one is for
Dr. Khan asked another question, right? Okay.
I went over both.
Okay.
Yeah, there is the first one here from Neda. He said, can this device automatically detect and count traffic incident in near miss events?
Yes, I think the amazing thing for this technology is you deploy there and you don't need to be watching it. It will be detecting the events and send, I mentioned this pilot project, with Yakima Nation, you detect the near miss or detect other things, you'll be sending that. Actually, since we deploy the sensor, there is another fatal crash captured by the sensor, exactly how it happened. They also get detected and labeled. So this can save a lot of human efforts, watching these things, right? If there's something need your attention, this section of road is covered by black ice. There is the warning message sent to the traffic operators. You can look at that. If you can, yeah, that's true. And then let me turn on the variable message sign to warn people, or I can reduce the speed limit, or I can even close the road, right? So I think this automatically detected traffic information will be hugely useful for real-time operations.
Thank you.
Okay. So before I give Dr. Okusiri, I know he wants to ask a question. Dr. Latiful Khan asks as well, if you could share your data set.
So Dr. Wang, will you be able to share the data set? So one of our researchers is asking whether you'll be able to share the data set.
Sure, you can contact, I can, you link to my students, who get the data. They have some data somewhere. I do not know where the data is, but certainly we could share.
Okay.
Satish, your hands up for some time. Go ahead.
Yinhai, great presentation.
Thank you.
Very interesting work. So I just wanted to get your take on this collaborative perception. Most of these applications are in real time, and that's where edge computing is really beneficial.
Mm-hmm.
But when you have a multimodal setting, each of these decisions have different latencies at which they need to operate. right?
Mhm.
And this sensing right now is not necessarily collaborative in the autonomous setting. So one, how do you address this challenge of this different latencies you have for multimodal decision making? And two, what do you think is the potential for collaborative perception in this, and what the challenges are there?
Yeah, I think the collaborated perception will also, I think, will be implemented better in this edge computing environment. And you could do the local communication rather than going through the cloud or the internet, right? So the local communication, you can guarantee, the latency is always predictable, rather than if somebody is sending a big chunk of data using the internet or the open network, your data will be delayed and the latency will be higher. So there are also technologies like federated learning. We're also working on that, and that could be a good way to really make the learning at different sides collaborative, right? So you don't have to be learning everything from each side, but there are also challenges. I intentionally put in several slides, but I look at that's too long a presentation. I cut them out. But I would say, Satish, I think the edge computing using methodologies like federated learning will be a good way to collect information, build a stronger model. And for cooperative perception, we have done some research. We plan to do some research with some transportation agencies very soon. So we try to capture the vehicle movement on a particular site beyond one camera's coverage, right? So when we team up with multiple cameras together and see the vehicle movements, predict the potential near misses or time to collision, that kind of thing will be very helpful for the transportation agencies. I think this edge computing approach I presented will fit this particular task much better than the cloud or the server-based approach.
I want to add one comment here. So Google has some patents on cloud edge collaboration. It came out recently. So they're using AI to decide which process should take place where, which will take place in the cloud, which will be on the edge, which as I reviewed it carefully, it has a great applicability for transportation system, edge computing. Google's patents.
Yeah, Google kind of company, they don't think in our style because they are basically very rich company with a lot of money, right? So we have to consider how we can make the system work in the best way with the lowest cost. And transportation somehow is a very important and critical infrastructure, right? So we certainly want to make the system relatively protected, not like everybody can access, and Google could make it.
You can follow the architecture. So it's architecture, you can use the architecture they proposed. So I think just as an input.
Maybe we can try that.
Yes.
But their architecture design normally is not considering transportation kind of application where we have the system relatively isolated. And how do you cross the boundary, right? If there's a regular, let's say, do the weather monitoring, right? So you put an edge there, you may have a cloud, bigger climate, like a climate model. I think that's kind of application to use the architecture suggested by Google, maybe easier, not like our transportation thing. I certainly need to be, I would say we need to be cautious to see if that will be fitting for this kind of like a relatively isolated system when collaborating with the open cloud system.
Okay. Any more questions?
I have one question, Dr. Wang. And it's more cybersecurity related with edge AI. Because you mentioned earlier that edge AI is limited in power processing, and you have to conduct some pruning in order to reduce the weight in the model. And once you reduce the weight in the model, AI model, that prone the model to be more vulnerable to cyber attack. Do you think that can be a big challenge in cybersecurity aspect of edge AI? Or how do you assess the robustness of the model, knowing that can be a vulnerability?
I think when we try to reduce the size of a regular model, we have to know what we're doing, right? So not randomly cut something. And when you try to reduce some of the capabilities, there's normally associated cost, maybe the accuracy cost or other thing. You have to balance, which particular branch to cut. So the impact of the final result is the minimum. I don't know if there's a general rule we can follow. In a lot of cases, you carry some fundamental thought and use your domain knowledge to try out and compare, right? So we have that flow chart I showed you on one of my slides, and that's something, a general approach. But when you do these things, try to make the operational efficiency better, it may also come up with a security risk. As I said, I'm not a cybersecurity expert, but I do count on you people to address these challenges.
I have a suggestion. Maybe while you prune, you cannot have like a robustness objective while you prune and do some adversarial attack to see how resilient the model is, so you can know where to stop. Because I know security is something that you should consider while you not on the operation, because that's a main part of the device itself.
Yeah, one problem, there's so many attacks that can happen. So you have to test on many different attacks. It's not only one type of attack, right? So.
Yeah, certainly the cybersecurity is an important thing. And as I said, the edge system may be more vulnerable to some attacks.
Yes, I can back that up.
People have some work to do.
Yeah, the processor is small, so you cannot have a very large cybersecurity model residing there. So, thank you.
Well, let's see if we have another question. Well, guess no one have a question. Well, thank you, Dr. Wang. Great presentation. We have learned a lot. And thank you everyone who participated today. And we will see you next month for our next webinar. Also, the recording will be available by Sunday. I will upload it on our YouTube.
Yeah, so the recording will be available on our YouTube channel. So thank you.
Thank you very much, Dr.
Thank you, Dr. Wang.
Thank you, everybody.
See you soon. Bye.
Bye now.